So for the last hour, we have Simon and Catterall, all the way from Syracuse University, New York State, 5 hours from every big city in New York, I believe. He's visiting us for next week's workshop, but he kindly agreed to give a colloquial talk about his expertise, which is lattice quantum field theory, successes and future challenges. Please take a look.
Thank you. So thank you for the invitation to talk here today. This is my first time visiting. In fact, it's my first time in South Africa. So it's been a very pleasant visit so far. So I got in last night, so it's limited, what I can say. So I'm going to, the goal today is to tell you, first about quantum field theory. So this talk is designed for a general audience, so it should be very low level. And I'm going to tell you a little bit about quantum field theory, a little bit about what lattice quantum field theory is, what it's achieved so far, and why it's now a kind of integral component to the international particle physics, high energy physics program. But also kind of that will sort of be the intro to the talk, but I'll also tell you where I think it can play a role in the future, looking for theories of beyond standard model physics. And so that's where I've spent most of my life, actually, not on mainstream so-called lattice QCD, but on these other issues. So I'll say something about that. That's the goal, anyway. Now it's not working.
No, it's not working, but I think I might just have the solution.
I can just go.
No, it should try now.
All right, yeah. I can always go over them. So here's an outline of the talk. As I say, I'll tell you a little bit about quantum field theory for those people who don't know anything about quantum field theory. I'll say something about the standard model of particle physics, and then why we need this thing called lattice, QFT or lattice QCD, to try to unravel certain aspects of the standard model. So a little bit of why and how we do that. And then briefly, I'll highlight a couple of recent successes of lattice QCD. And I'll use that as a springboard to then discuss sort of new directions or new things we can do with lattice quantum field theory, which have impact potentially on new theories of physics beyond the standard model. So I'll talk very briefly about supersymmetry and holography, whatever those things are, you'll find out, quantum gravity, and then alternatives to the basic Higgs scenario and how the lattice can play a role in saying something about those things. All right, so first of all, what's quantum field theory? For those of us who don't know, so this is a sort of a fairly well-known sort of picture that shows how the typical theories of physics can be parameterized in terms of the Newtonian gravitational constant. So this is like a cube in theory space. So here on the vertical axis here is the gravitational constant. Here is the speed of light. Then coming out of the page is h bar, Planck's constant. So classical mechanics, the sort of things you learn about in intro physics, sort of lives in this corner down here, where basically the speed of light is infinite, h bar is 0, and we don't worry about gravity, right? So that's where classical mechanics, blocks on planes lives. If I switch on the Newtonian gravitational constant, then I can talk about Newtonian gravity, things like the solar system. If I go along here on this axis here on the and use a finite speed of light, of course, I then have to incorporate the effects of special relativity. If I go out along here, this axis here, then I'm building in quantum mechanics. I can start combining these axes. So, for example, I can include, for example, relativity with Newtonian gravity and end up with general relativity in this corner of the cube. But quantum field theory lies down here, where I switch on a non-zero value of h bar and a non-zero value or a non-infinite value of the speed of light. So it's a natural merging of quantum mechanics and special relativity. All right, and it's sort of inevitable when you put quantum mechanics and special relativity together that you end up with quantum field theory. And so it's very obvious it plays a role in elementary particle physics but it also is used in many other aspects of physics. It turns out whenever you blend these two things together, you're not really talking about a theory of single particles, but many particles in general. So it's used in nuclear physics and in condensed matter physics to handle many body effects where there's a varying number of particles in the system too. So it actually has a very broad role beyond just the applications you might think of in high energy physics. So first of all, we have to sort of say a bit more about what a field is, and specifically what a quantum field is. And so the classic example of this is to think about the electromagnetic potential. So to think about Maxwell's equations, all right? So I'm being a bit schematic here, but you know that in principle, I can take the electromagnetic potential. I've written it as a function of x and t here. You can think of x as representing x, y, and z if you want. And I can Fourier expand it, right? I can just imagine decomposing it onto a bunch of modes labeled by a wave number k, or a wavelength, right? And each of these modes, if I plug this into Maxwell's equations, I'll find that each of these modes, A, K, satisfies a harmonic oscillator equation. Right? So each mode is a quantum oscillator, the field, right? So I start with a continuous field, I expand it into modes, I notice that each mode satisfies a harmonic oscillator equation, and I know how to quantize that system, right? I already know the answer here from ordinary quantum mechanics, the sort of thing you learn in a first quantum mechanics class. You know that the energy of that mode goes like n plus a half times h bar omega k, where this is the frequency. In this case, the frequency is just related to the wave number for a massless sort of electromagnetic field. And then if I want the total energy of the system, I just sum over all the modes, right? So, but the key thing is, because this has an integer spectrum, I can reinterpret the nth energy level of a given mode as corresponding to the presence of k photons with that wave number. So this is only allowable, or only a reasonable interpretation, because I have this integer spacing of levels. So I can think of the nth level as corresponding to n elementary excitations, which we know as photons in the case of the electromagnetic field. Right? So in other words, a dagger on the ground state, the vacuum state of the theory, gives me an elementary excitation of a field which has a finite discrete energy, and we call it a photon. So this is the paradigm example of a quantum field theory. I take a classical theory, I decompose it into modes, and then I just apply what I already know for the quantum harmonic oscillators to that mode. Okay? And that way I discover the elementary excitations of the field have a discrete-like character, and those are, if you want, the elementary particles. So this game is played in quantum field theory for all types of particles. All particles are assumed to be elementary excitations of some field, whether it be a quark field, or the electromagnetic field, or some other field, force field. And of course, once I do this, these A's and A daggers are operators. So you should think of this object, this psi, which is the analog of A, as some sort of generalized quantum operator, which is used to create excitations out of the vacuum. So you see, in some sense, quantum field theory is not particularly unusual. It's really an application of what you already know about quantum mechanics, the case where you have an infinite number of degrees of freedom, that is the modes of the field of CERN. So the key thing is that every particle is meant to be an excitation of some field, which in principle extends throughout the universe. So the identity of all particles is guaranteed because they're all excitations of the same underlying field. If it's a quark field, for example. Right? So particles aren't fundamental, it's fields. That's the first point. But those fields are very natural things to arise in a theory which wants to describe things which have both wave-like, that is continuous, and discrete character. So wave-particle duality is just automatically built into this. Okay. Okay, so the standard model is a bunch of these quantum fields. It's invariant under a particular symmetry. I won't go into a huge amount of detail here, but it has...
on the previous slide. So when you say these are all oscillators, so where do the non-perturbative nature?
So in the interactions. So this is all free fields. Right. So at the moment, I haven't introduced any form of interaction. It's absolutely crucial that all the free fields in the world basically give you rise to harmonic oscillator equations of motion. How those fields then interact is a separate business, and we'll talk a bit about that. All right. Okay, so this theory has a certain symmetry, and I'll say a little bit more about that. But if I think about these, the symmetry associated with SU3, this is the special unitary group. What that really implies in practice is that a given, say, up quark in the theory, right? That's an excitation of the up quark field, has three components. You can think of it as red, green, and blue. And so what happens is, in the Hamiltonian I would build describing the interactions of these quarks, I'm allowed to replace the original set of three fields by any linear combination of them where this matrix M is a 3x3 unitary matrix. Right? So the theory is invariant if I do this rotation of one set of quark fields into another set, these U prime fields. That's the statement that it has an SU3 symmetry. This is actually what's called a gauge symmetry. And what that means is this matrix M can be chosen independently at each point in space and time. Right? If you do that, this determines the kinds of interactions you can write down essentially uniquely. So the choice of symmetry group here, the fact is the Hamiltonian doesn't depend on these global rotations of quark fields into each other. If you gauge it, that is, you make sure that you can do this locally at every point in space-time and still leave a Hamiltonian invariant, that essentially determines all the structure of the interactions. I won't go into the details, but that's sort of crucial. So these up quarks just live up here. There are equivalently down quarks. The SU2 symmetry basically mixes those two guys together. It also mixes the electron with the neutrino. So this first column here is the first family of elementary particles. For some reason we don't understand, it's duplicated 3 times. I won't have much to say about that in this talk. And this fourth column here labels the kinds of force-carrying fields we need. So we know there's a photon in the game. There's also a W and Z boson associated with this. Boson sitting on separately. Okay, so that's the basic structure of the fields that we think are important for describing the elementary particles that have been discovered so far in nature. They all form, hopefully that's not super important. They all basically are associated with parts of this table. And the point is that the quantum field theories describe these elementary excitations and their interactions all satisfy a certain symmetry. And that symmetry is gauged, which means that those interactions are determined somewhat uniquely. Can't just write anything down. If I want to calculate with these QFTs, then I have to put interactions in. And so Anna's just questioned before. So a typical interaction term, for example, would couple, say, a quark, or let's just think of it as in the context of the U1, the electromagnetism. So I take an electron and its antiparticle in this case, and I couple it to the photon and integrate over all space with some coupling constant G. That would be a typical allowed interaction term between electrons and photons, for example. That satisfies one of these gauge principles. And if G is small enough, you can expand the effects of this interaction term in what's called a Feynman diagram. That is, an electron can come along, and at some point it can radiate a photon, which can then interact, in this case, with a quark antiquark pair, or it could be another electron positron pair here. And so the effect of these interactions can be calculated sort of as a power series in G. That's called perturbation theory. And the weak and electromagnetic interactions are well understood by writing down diagrams like this, which calculate the effect of the interactions to some small power in G. So this would be G squared. There'd be a factor of G here and a factor of G associated with this vertex. Okay. This process has been very successful for electromagnetism, and I'll have something more to say about that later when I talk about the view on G-2, and also for the weak interaction, but it fails horribly for QCD, this SU3 component to the symmetry, because this G is order 1. So the expansion in powers of G doesn't make any sense, and complicated diagrams outweigh simple diagrams in a naive way. So you simply can't just approximate the effect of the interaction by some simple low-order Feynman diagrams. You're going to have to do something else. And so that's where people have turned to using numerical methods. And the numerical method is called Lattice QCD in this case. So I'm going to say something about Lattice QCD in the next few slides, what it actually means, how we go about what it looks like in terms of a theory, and how we calculate with it and what the results have been of those calculations. Right. So I'm just focusing on this SU3 sector of the standard model for the moment. If I want to put it in a computer can only handle a finite number of degrees of freedom by definition. One has a finite memory. So the first thing I have to do is get rid of the fact that x, y, z, and t are continuous variables and replace them by some sort of four-dimensional grid in space-time, a lattice, in other words. So the quark fields that are important here would live generally in these approaches on the lattice sites. And then the photon, the analog of the photon, which is called a gluon here, would reside on the links between those lattice sites. Okay. So on each lattice site, I have to specify this psi field, right? So to give an x, y, z, and t, I have to specify what psi is. It carries several labels. It carries a spinner label because these quarks have spin, right? So it's you have a four-component spinner structure. You learn that from studying the Dirac equation, which is the relativistic analog of the Schrödinger equation. But they also carry this color label A, which runs from 1 to 3. So I have 12 basically complex numbers at each lattice site. That's the first point. And these U fields here are precisely like those that operator M I wrote down before. They carry labels A, B, where A and B run from 1 to 3. So they're unitary matrices which on the quark fields living on the lattice sites. They also carry an index mu because this tells you about direction because they line a link. The linkage has 4 directions in space-time. So you don't have to take this to understand this in detail, but roughly speaking, the Hamiltonian, or more precisely the action that is used to simulate these theories, has a construction where the psi's are linked together by these U operators, which carry the gluon fields in them. And then there's also some Dirac gamma matrices floating around to soak up the spinor indices. And I have to sum over all points in space, time, and all directions n, or mu. And there's a bit more structure here which I've left out, but that's the basic idea. So I can write down something which is like a Hamiltonian for the system, living on this discrete grid, and then eventually I'll be able to do numerical work with that Hamiltonian, or this action in this case. Any questions?
So this term already contains trace of.
No, it does not. That's in the dot, dot, dots. And so I have to write a separate piece for the gluons that gives you the gluon kinetic energy. This is just the interaction. This is the hopping term for the fermions, the kinetic operator for the fermions, and the interactions with the gauge field. So they're all contained in this because this is locally gauge invariant. But I haven't written down the kinetic operator that governs the propagation of the gluons. That's in the dot, dot, dots. Okay, so this is obviously a grid only in 3 dimensions because I can't draw 4. Right. So how do I go about simulating this system? I want to use sort of non-perturbative methods to do calculations now. So what I do typically is I use Feynman's observation that any matrix element that you want to compute in the quantum theory can always be gotten by a so-called path integral, where I integrate over all the field configurations. I stick the operator I'm interested in here, and I weight them by some exponential of this action I wrote down. You can think of it as like a Hamiltonian. In Euclidean space, it's basically the same thing. So in fact, anything I want to compute can be computed by estimating what this integral is. Right? So it looks a lot like statistical mechanics, where h bar is playing the role of the temperature. You might have, if you know a little bit more about Feynman path integrals, you say, well, shouldn't there be an I sitting up there? There is an I in general if I'm in Minkowski spacetime, but typically these calculations are carried out in what's called Euclidean spacetime, where I replace the time by imaginary time. And that converts the I, removes the I, and gives you something that looks like a Boltzmann factor here, guessing temperature. So the point about this reformulation of the theory, so that I can compute these operators I want on the left, is that this thing can be sampled using standard so-called Monte Carlo methods. So I can sample, I don't do the integral exactly, I can sample from it, treating this e to the minus s as a probability distribution on the space of field configurations. Right? So there are algorithms for making small changes on these generic fields phi, which allow me to explore the most important contributions to this integral, and that will estimate the integral and estimate these expectation values. The tricky part is the fermions. And there's a standard algorithm in the RHFC algorithm. I won't go into the details of what this algorithm is, but all you have to realize is that the operator that couples the fermions, psi and psi bar, the thing I just showed you, in general is a large sparse matrix. In fact, for typical state-of-the-art calculations, it's a matrix just 1 billion by 1 billion complex numbers. So it's an enormously large matrix, and you have to make the Monte Carlo, roughly speaking. So you end up solving a linear system of size 10 to the 9 by 10 to the 9 many times to come up with a single Monte Carlo step. So this is extremely numerically hard work, but nevertheless, if you use GPUs and parallel programming and you run on sufficiently massive machines, so this is the Frontier machine at Oak Ridge, does something like 10 to the 15 floating point operations per second. If you employ all this technology, this hardware, you can actually do a reasonable job at estimating these intervals. That's the take home, right? And these are the intervals you want in order to compute quantum effects in a quantum field theory on a lattice, right? And at some point, you have to shrink the lattice spacing to 0 and talk about the continuum limit, which is where you think you live.
So those are approximations to discrete lattice.
So this Monte Carlo estimates approximations to the discrete theory. So I have to worry about statistical fluctuations in the Monte Carlo, right? So everything I compute will have an error bar on it associated with the fact I only sampled this a finite number of times. And then in addition, I have to worry about shrinking the lattice spacing to 0 to talk about the continuum quantum field theory that I'm interested in. And in addition, I have to be careful what questions I ask. I can only ask sort of time-independent questions because I've rotated my time coordinate to imaginary time. So I can ask questions about energies, but I can't ask questions about real-time scattering, at least not directly this way. So but nevertheless, Monte Carlo is an extremely efficient algorithm for sampling this interval and basically doing a calculation in a Hamiltonian formalism, which would be extremely hard to think about even. And in a sort of conventional approach to mechanics based on Schrodinger's. Okay.
How long will these calculations usually take?
Oh, months.
Months.
So yeah, you know, you're talking about generating at least petabytes of data over many months in runtime. Right, so this is the biggest supercomputer right now in the world. And now QCD doesn't get a huge slice of it, but still. It takes time. And collaborations now involve scores of people working for 2 or 3 years, typically on a typical calculation.
I was about to ask how big are these?
Well, they're not experimental in size, but they are grayed down. So, you know, 10 to 20 people is not unusual. And there are people who are very good at writing the code that you need. And there are good people who are very good at doing the analysis you need to extract the physics out of the the Monte Carlo simulations themselves. So it's a big process. This has been going for 30 years. At this point, it's pretty sophisticated, as you'll see, in terms of what it can produce. But it's not a trivial calculation. It's on the scale of a small experiment, small energy physics experiment, which is already not a small experiment, right? Okay, so let me give you a couple of slides, sort of showing you the kinds of successes that have been achieved with this sort of approach. So the first one, and it goes back really to Ken Wilson, who was a Nobel laureate for this work, given it in 1982. When you reformulate the theory in this discrete form, there are things you can do even analytically before you do numerical calculations, which allow you to understand certain features that are not otherwise obvious. And the key feature that you can immediately pull out of this reformulation of the theory on a discrete lattice is that quark confinement takes place. So if I look at QED, this is the field lines for QED, say between an electron and a positron. They have this sort of generic form you find in your undergraduate textbooks. If this coupling constant gets very strong and the interactions have a particular flavor which is natural for QCD, what happens is these field lines get compressed into tubes connecting now quark and an antiquark. And as I pull the quark and antiquark apart, clearly the energy density increases roughly linearly with the length of the tube, right? So this is the process, and you can see this in what's called strong coupling expansions almost immediately. It's the leading order strong coupling result for the theory is it predicts this linear confinement of quarks. So this is in Ken Wilson's original paper in 1974 on confinement of quarks. This is essentially really what, well, he got the Nobel Prize for many things. Okay, and here's a not particularly recent, it's probably about 10 years ago, a plot of the hadron mass spectrum that you get by simply, so here's the linear potential. By the way, this potential between quark and antiquark, and you see it numerically coming out, but you can see this, the effect of this thing is even visible in leading order in strong coupling. So expansion in 1 over G, not G. You can't do an expansion in 1 over G very easily analytically, but you can certainly do it numerically. What you see is, this is the hadron spectrum. The points are the data points, the experimental numbers for the different mesons and baryons, and you can sort of see the horizontal error bars tell me roughly what the numerical result comes out of QCD. So you see the experiment, the agreement is generally extremely good and always within the error bars. These days, these error bars for many of these quantities are sub 1%. Right, so you start off with a unique theory, which is specified basically just by the quark masses and the gauge coupler, so 2 or 3 parameters. You run it, you can generate an infinite number of hadrons, and they all agree with it. Nowadays, an order 1% error. That's the typical situation. That's it. So to do the, I don't know what they used to done on this. This is 10 years ago, so this is probably 60 to the 4th. 60 times 60 times 60 times 60. But the current lattices are more like 100 plus.
Is it surprising?
I don't know whether it's surprising or not. I mean, one thing I should hit the right numbers. So you have to specify the input U and D quark masses and the gauge coupling. So you have to specify 3 numbers, and you do that by measuring this numerically and making sure these line up. That fixes these guys, and then everything else in red follows from it. Okay, so the fact these agree perfectly is by design. So you fix the pi, the k, and the omega in this case. There's a big history behind producing plots like this and improved plots, but of the same type of thing. You have to be sophisticated how you take the lattice spacing to 0 and take the volume to infinity. There are various things that are going on in the background here, which I haven't time to talk about. There are extrapolations that go on besides, you know. So you have to take the continuum limit, and you also have to take the large volume limit to get these kinds of results. As I say, this is not a particularly recent plot, it's just one I could easily grab. It's probably at least 10 years old. Nowadays, things would be even better, actually. People have given up doing the hadron spectrum because it works, right? So it's not considered a current forefront thing to do. It's something you do on the side when you've got your configurations and you want to get as much out of it as you can. But it's not where this field lies. This is closer to what's been very successful within the last 10 years. So people have been trying to understand the weak interaction in more detail. There are various parameters in the model of the weak force, specifically what's called the CKM matrix, which is specified by these V's here. So they have 2 indices, A and B, so they're kind of matrices. They tell you the mixing basically between the B quark and the U quark. So they're parameters in the standard model. You would like to measure them because a priori you don't know what they are. You can measure them by looking at experiments that measure, say, the decay of a B meson into a K meson. So a B meson has a B and an S quark, and a K meson has a U and an S quark. So what's happening in this decay is a B quark is turning into a U quark and radiating a W boson, right? And the point where this is a Feynman diagram here, there's a coupling constant goes in here, and also this factor of VUB. So you'd like to measure VUB. The problem with this is that this is the simple sort of Feynman diagram from the weak sector, but this B and S quark don't exist in a simple pair, right? They are dressed by QCD. This is a full meson, so it's a more complicated, strongly interacting system. And so the amplitude for this process factors into a piece which depends purely on QCD, and a piece which you get in perturbation theory for the weak interaction. If you want to extract V from this kind of experiment, you have to compute this factor numerically and then access the V that's living inside an A weak. So this has been a program which has been going on for more than 10 years now. It's probably 15 years. At this point, Lattice QCD can compute this factor to within about 1% for typical meson decays. And that's allowed us to extract VUB and test whether indeed this matrix is unitary and things like that. That's now known to be very accurately the case. precisely because we have this tool, Lattice QCD, which allows us to get at these pieces. If we didn't have this Lattice QCD, this decay would not be able to isolate VUB, say, in this case, this V matrix from the data, because it's convolved with the QCD interaction. And so you have to compute that theoretically separately. Right. And this is related to interesting things like CP violation, of course, because the phase in the CKM matrix is one driver of so-called CP violation. That's related to the fact that there are more particles than antiparticles observed in the universe. So this is very important from indirect probes of things beyond the standard model. So you need to understand what the standard model says about CP violation before you can look for excess CP violation from beyond the standard model physics. So that's been a huge success. A very recent success in the last, say, 5 years has come from this measurement of the magnetic moment of the muon. So there's been a lot of very successful experiments carried out initially at Brookhaven and more recently at Fermilab, which compute this factor G, which tells you how big the muon's magnetic moment is in units of E/2m in this case, right? So if you go to the Dirac equation, you can read off the magnetic moment of the muon as just G = 2. This number is 2, right? So the muon has a spin, an intrinsic spin. It interacts with an external magnetic field and generates through a magnetic moment. And you can measure that interaction frequency results and extract this G from it experimentally. So from experiment, this is the number. So notice it's known to like 10 decimal places. So these experiments are incredibly impressive in themselves. They're able to measure the deviation of G from 2 due to quantum field theory effects to that kind of accuracy. All right. Now, if you go to the Dirac theory and say, well, how does quantum field theory correct G? Because G is clearly not 2. It's down by at least a factor of 10 to the minus 3. It comes from quantum field theory corrections, those kinds of Feynman diagram things we talked about before, but it also has a contribution from QCD. And this is where the lattice, again, has had an important role to play. So this picture down here, somewhat old, but it roughly shows you what the situation was in 2020. So here's the experimental number inside this green band here. This was the theory prediction for G-2 back in 2020. So there's a white paper here. And so you can see the theory prediction and the experimental data were a long way apart, about 4 sigma. So this looked like a tension between the standard model calculations that went into this blue band and the actual experimental numbers. If you look in 2024, you'll see, so this is the most recent Fermilab result here in 2024. So it's basically not really changed much. The experiment has gotten a little better. So this is the old Brookhaven result. This is the Fermilab result. This is the combination. But what you see is suddenly the theory, which is given by this red bar, has moved up to be completely consistent with the experiment. So from the perspective of BSM physics, this is kind of boring. There actually isn't any sign of BSM physics in the mu1 G-2. But the reason the theory result has gone from here to here is entirely a function of Lattice QCD. So what happened is they get good at computing these hadronic vacuum polarization bubbles using lattice methods that give you the main contribution from QCD to the mu1 G-2. I won't go into here's the experiment. I won't go into the details at all, but you just have to realize this is a tremendous kind of success of Lattice QCD. Without Lattice QCD, they had a way of computing, they thought, the hadronic vacuum polarization using phenomenological methods combined with experiment. All those methods agreed and gave you this number. All the lattice methods these days, basically, now many groups have done this calculation in the last few years. They all line up here, very close to the experiment. So the different groups are agreeing. There's a lot of consistency, but they all disagree with the original phenomenological estimates.
But does it teach us also what's the That's the lattice.
No, it's actually so the groups that are responsible for this number have still not figured out why they got the wrong number. They were all agreeing with each other. There's been a more recent experiment. So this takes experimental input and massages it using basically something like the optical theorem to give a prediction for this bubble. So it depends on both experiment and pheno modeling. A new experiment has been done which pushes this number much further up, but they don't know why the new experiment differs from all the old experiments. There were half a dozen of these things. And they don't know what's going wrong exactly in the original analysis. So when people talked about using Lattice QCD to do this, to play a role in this resolving this problem, they thought this piece was understood well enough that the Lattice QCD would have nothing to say about this. And they were worrying about something called the light by light contribution, which was a much smaller contribution, but was something they couldn't get at phenomenologically at all. It's turned out to be completely the reverse. The lattice has done the hadronic light by light, and it's down to about 10% accuracy. It's a small contribution, and there's no problem with that. What's happened is they found the hadronic polarization piece was actually very different from the phenomenological game. So it was thought that Lattice would not be able to do this well enough to beat these guys. It's actually done better than these guys, and in fact shifted the number completely. Yeah.
So what scale is this measurement being done? Is it MeV time scales or is this at very high scale? So usually one has.
No, it's sort of NEV scales.
QCD is important.
Oh yes. Yeah.
But is there a way of kind of doing something similar at higher scales for the games? Or does it involve having static kind of?
I don't know. I actually don't know. I'll just be honest with you. I'm sure this is part of the discussion. They must be still trying to understand what's going wrong with this.
Will go down at higher scales.
Yes, but I don't. But I think in the relevant scales for the mu and G minus 2, it's still very important. So it turns out, people originally said Lattice would have nothing to say about this. It was already being done well by these guys. You should worry about this other contribution. It's turned out, in fact, that their estimates were all wrong. This has turned out to be crucial, and it's moved the theory up completely by 4 sigma. So it's actually it's still ongoing. People are still doing analysis, but I consider the problem solved. This one, there's nothing interesting in the mu G minus 2, unfortunately. All right, so it's gone from this. Lattice QCD has gone from what is a conceptual tool for talking about strong coupling and thinking about quark confinement as a conceptual problem. The emergence of this linear potential between quarks and antiquarks, to now a high precision tool that's crucial for the experimental particle physics program internationally. Without it, you would not be able to say much about flavor physics, and you certainly wouldn't have resolved, for example, so that's all still going on, but the point I want to make in this talk is that there's a lot more that Lattice QFT, generally speaking, can do in the search for beyond standard model physics. So that's what I want to turn to now. Okay, not too bad. All right, so the kind of challenges that we can think about trying to use lattice methods for are kind of overlap strongly with things we don't understand about the standard model. So, for example, we don't know, well, the standard model does not include dark matter and dark energy, and we'd like to have some, understanding of that. We really don't understand why the Higgs is light. I may have time to say more about that later. So the Higgs sector works beautifully in the standard model, but it seems from a theoretical perspective very unnatural, primarily because the Higgs is much lighter than you would have guessed. We don't know why there are 3 families, and we don't really understand where the major components of CP violation are coming from, whether there's some evidence for sterile neutrinos. But again, that's something the experiments are focusing on at the moment. And we don't really understand whether the standard model forces unify at some high energy gut scale. We'd like to understand those kinds of things. And of course, there's this whole issue of quantum gravity, which has been a thorn in our side for many, many decades. Right, and what I want to sort of emphasize to you is that the lattice quantum field theory, as opposed to lattice QCD, can play some important role in addressing many of these problems. And I may talk about things that touch on the red dot points here. I probably won't have much to say about, for example, why there are 3 families. All right, so let me move on to that. So the first topic I thought I'd talk about, something I've worked on personally, is this idea that gravity is in some sense holographic. That means that there's an equivalence of gravity in curved space to quantum field theories living on the flat boundary of that space. So the classic example, which goes back to Maldacena in 1998, is the so-called n = 4 theory that I think several of you are hearing lectures on this week. So n equals 4 supersymmetric Young-Mills is meant to be dual or equivalent to some form of string theory, or in low energy supergravity in a 5-dimensional anti-de Sitter space. Okay, so I have to tell you, for those who are not experts here, what I mean by supersymmetry for a start. So what I mean by supersymmetry is these theories, this n equals 4 theory, has an unusual symmetry which allows me to turn bosons into fermions, right? So it's a sort of uniquely defined symmetry with that property. It's crucial to showing this equivalence here. And so it will, if we want to do something on the lattice, we have to include a lattice theory which is capable of exhibiting some amount of supersymmetry. That turns out to be a non-trivial theoretical problem. In addition, what is anti-de Sitter space? It's just a space, a maximally symmetric space with constant negative curvature. So those are the two key ingredients that in this particular version of holography. So what is this n equals 4 theory in a little more detail? It's like the QCD theory I talked about before, right? So it has the analog of gluons in it. It has the analog of fermions in it, just like in the standard model. It has some additional scalar fields, which I won't write down. And to make the connection to gravity, I have to generalize the 3 colors of QCD to a general number of colors. But roughly speaking, it's like QCD with some bells and whistles added on. The n equals 4 bit just tells me there are 4 supersymmetries in the theory, not just 1. Now, the problem in general in putting these supersymmetric theories on lattices is that if I take the product of 2 supersymmetries, what I end up with is generally an infinitesimal translation. And so when I lattice space by putting a grid on it, I have no longer any infinitesimal translations left. So typically, if I just try to take a theory like n equals 4 super Young-Mills and stick it on a grid, I will break supersymmetry right from the outset because I don't have any exact conserved supercharges typically. All right. And so what that means is I take the lattice spacing to 0, I won't flow back to a supersymmetric theory at all. So I have nothing to say about n equals 4 if I just try to look at this theory naively using the techniques I just told you before. So the trick of making a supersymmetric lattice theory out of this is to try to find linear combinations of these 4 supercharges, which have an unusual property. So I'll call them curly Q. They have the property that when I do 2 of these guys, I do nothing at all. So this is what's called a nilpotent symmetry. So the trick initially is you have to reformulate the original theory. If you want to stick it on a lattice and keep supersymmetry, you have to reformulate it so at least one set of supercharges have this property. When I do them twice, do a supersymmetry variation twice, I do nothing at all. This is called a twisted theory, and it's crucial for writing down a lattice theory which keeps the supercharge exact. So the idea is that if I can keep it exact, then the bosons and fermions are paired even at non-zero lattice spacing. And that eliminates most of the problems you would have in taking the continuum limit and getting back a theory with full supersymmetry. So I won't go into the details of this theory, but it's a little different from what I said before. We still have gauge fields living on links, but in general, these are not unitary matrices anymore. They are just complex matrices. The fermions no longer just live at the lattice sites in these constructions. They live at the sites and on the links and on the faces of the lattice. So they live on higher dimensional objects than just sites. The construction that we've been using also self-consistently determines what lattice you must use. So instead of just using a square lattice like it would do with QCD, the natural lattice here is what's called A4 star. So it's kind of an analog of the triangular lattice now in 4 dimensions. So you can write down a lattice theory using these kinds of ingredients, which corresponds to n equals 4 as I take the naive continuum limit. It conserves one exact supercharge at non-zero lattice spacing. And it has a very high point group symmetry, like this has a higher point group symmetry than usual cubic lattice. And that's actually crucial when you look at how the continuum limit is to be taken. So using this construction, you can actually go check some of these ideas about holography. So for example, if you reduce the dimension from 4 down to say 2 or 3 or even 1, you can predict. Well, maybe I won't even do that for this. That's what this plot is about. This is actually in 1 dimension. You take this construction and project it down to 1 dimension. it tells you there's an agreement between this dotted curve here, which corresponds to the leading order supergravity result, right? This is the energy, basically the energy of a 5-dimensional black hole. Actually, it's a D0 brain, actually, in this case. These are lattice results. This is from about 10 years ago, actually, so they're not actually recent, where we've run up to SU16 here. And you sort of see as you get to the green points, you're starting to sort of lie close to the line. These are all pretty small lattices as well. You have to take the limit as NC goes to infinity to make this equivalence exact. But you can sort of start to get a hint. These are measurements in a flat space super Yang-Mills theory. There's no fitting here. This curve is determined entirely by the supergravity theory. So you either lie near it or you don't lie near it. You either functionally follow this curve or you don't. So the point is that while this is well understood in the limit n goes to infinity and strong coupling, it's actually not understood in general away from large n. And the lattice in principle can easily probe the quantum gravity corrections that are potential corrections to this leading holographic result. And that's something that we've been involved with over the years for quite some time. The most recent paper is this one, where we actually compute the static quark potential and show it agrees with the results of holography and their leading prediction from Al-Hussein from many years ago. All right, so that's one thing you can do. But when I think about gravity more generally, you might try to explore an old idea. Suppose I put string theory on one side and holography and just think about quantizing gravity directly. You can try to do that using the Feynman prescription of writing a path integral for gravity, where I integrate somehow over metrics weighted by some factor depending on the action for a given geometry. So this is the Einstein-Hilbert action. That's a simple example of what you might look at. Now, this is the famous theory, which is completely non-renormalizable in perturbation theory. So there's little you can do with it in perturbation theory. There are lots of infinities and you can't cure them. But it's an old idea due to Weinberg that somehow this problem might be a problem of perturbation. That this theory actually might have a fixed point in the UV where G is away from 0. So it's not expanding around G equals 0, but some other point where it's perfectly renormalizable. And so what that would mean in the lattice theory is that the theory would have a continuous phase transition at some non-zero value for the couplings, right? So it's an old conjecture, and the question is, can you actually numerically check for that? How would you do that? So you have to use lattice methods because the guess is that if this happens at all, it happens only at strong coupling. So you have to use a non-perturbative method to look for this problem. And so people have tried to do that, including I did this years ago, but then I gave up and did something else. But my colleague is actually very actively pursuing this direction. So what I'm going to show you now are his results, not mine. First trick is that you have to think about what you do to replace this integral over metrics. So the simplest thing you can think about is I sum an out over triangulations of some 4-dimensional space, Euclidean space. Right? So my partition function thing I want to compute or estimate using Monte Carlo is some sum over triangulations. So each triangulation somehow uniquely picks out a geometry in the space, a gauge fixed geometry in the space of all geometries. So the idea is these triangulations are completely equilateral. They're built out of simplices, 4-dimensional simplices, which are taken equilateral. So they have a single lattice spacing. You glue them together in all possible ways consistent with the topology, and that's what you mean by the sum, and that's meant to integrate. That's meant to be the gauge fixed version of that integral over metrics. It's a conjecture. In 2 dimensions, this conjecture is correct. In high dimensions, it's purely nonsense. So you have some version of the Einstein-Hilbert action, which depends now on the trial. Sorry. Where else? So you have some version of the Einstein-Hilbert action. It turns out on these equilateral triangulations, this reduces it to something very simple. It counts the total number of 4 simplices. That's like a cosmological constant. And there's a piece proportional to, for example, the number of 2 simplices, that is triangles in the system, with some coupling constant kappa 2, which is like a bare version of the gravitational constant. And you might think about adding higher derivative terms as well to it. And in fact, you need those. So the coupling constant here is important beta. But these are marginal operators you can add to the Einstein-Hilbert action, and you probably should. So what you find is, so let me step back. So I want to Monte Carlo this thing, right? So I need to be able to make small changes in the configuration space of the system. The configuration of space of the system here is the abstract triangulation. So I need to be able to make small changes in my triangulation correspond to small changes in the metric.
Oh, sorry. So the discretization doesn't cause problems with diffeomorphism?
It breaks it. All you have is relabelings of the triangulation. So the idea is that you're factoring out the diffeomorphism group by precisely the ansatz by just taking a given triangulation that corresponds to a whole diffeomorphism equivalence class of continuum metrics. Now that's in 2 dimensions, that's a precise statement and it's correct. In 4 dimensions, it's purely an ansatz and it may be wrong. Right?
Is there a good measure?
No, well, so the measure is what this is the measure. You've made a choice of measure. I'm going to pick, equilateral triangulations of 4-dimensional space. Suppose I take it to be S4. So the 4-dimensional sphere, I want to integrate or sum over all possible triangulations of the 4-dimensional sphere built from equilateral simplices weighted by this particular Euclidean action, which is meant to represent the Euclidean Einstein-Hilbert action restricted to. So it's an ansatz, I think. You can do this Monte Carlo procedure because it turns out that in any number of dimensions, there are natural local moves you can make on the triangulation, like, for example, inserting a point. This is in 3D because I can't draw 4D. If I take a tetrahedron, which is the elementary building block in 3D, so I would be gluing tetrahedron together across spaces to build up the triangulation. I can always take any at random one of those tetrahedra and insert a point in the center of it and reconnect it out. That gives me a local retriangulation. I can also take, here is 2 tetrahedra glued along a face. I can delete the face and insert a link here, which gives me 3 more tetrahedra around the link. That's another local retriangulation. You can prove that these are ergodic and will get you from any triangulation to any other triangulation. So you can use them in a Monte Carlo procedure by randomly trying to do them, seeing how it changes the Boltzmann factor, and accepting or rejecting the change. It gives you a way of estimating that partition function. And so when you do this, typically, you will find a region where all the geometries collapse into high connectivity configurations, sort of Planckian scale if you want, so-called collapse phase. There'll also be typically a region where the geometries are long and stringy and branch palmar-like. They look almost 2-dimensional, not 4-dimensional. And then there's a critical line that appears between these regions. And as you go down the critical line, there's sort of a latent heat of the system is decreasing. So there's a conjecture that somewhere, maybe at infinity along this line, the latent heat goes to 0 and there's a continuous phase transition between a collapsed and an expanded geometry, which may have something to do with 4-dimensional Euclidean quantum gravity. That's the experimental fact, if you want. Or it may be some other interesting theory. Right. So let me show you that it's not completely crazy. If you restrict your topology of the space to something like a sphere, that's of course Euclidean de Sitter space, then you can simply sit at a random point in your ensemble of geometries and count the area you reach as you make r steps out from that point. So that's known what that looks like for classical de Sitter space. It's this black curve here. Right? So it has this sine cubed r root lambda dependence for a classical de Sitter space. These colored points are what you find on the ensemble of geometries. And as you go, as you notice, you have a long tail typically. It's like this red curve. But as I change kappa 2 here, that's the gravitational constant, I can push that tail in and in as though and it looks like it might be converging towards the true de Sitter result in the limit. Now, what you're doing here is you're moving down that critical line. So as I change in the kappas here and the corresponding betas, I'm actually keeping along that critical line where we see a phase transition. And so what you see is that it's consistent that you approach something close to classical de Sitter space as you take the continuum limit in this problem. Okay. Right, so this is results by Jacques Leo, my colleague from just recently. So beta was that curvature color. If you want, as a generic R squared. He talks about it in a different way, but I think you can just think about it as the coupling to. There are really 2 R squared operators you can add. He's only adding 1 right now, effectively, but he's tuning kappa. So this is meant to be kappa 2, the gravitational constant. Beta is the vertical axis, and you find this critical line in the combined phase. Yeah, Ricci squared. The way it's parameterized in the code is a little different, but that's basically the idea. Okay, so that's interesting. You can also play a game.
This
is just saying that so the fact that there's potentially a continuum limit, that if I go down this critical line, which has a first order transition, but it looks like a first order transition that might end in a continuous fixed point, the presence of a continuous fixed point would be the statement that the theory, well, has a non-determinate fixed point, which may or may not be the Weinberg point. So it's, the renormalizability in lattice theory is with the statement that the theory has a continuous phase transition. So what you're looking for is evidence that some lattice theory has a continuous phase transition. In QCD, it's trivial. We know where it is. It's G equals 0. So you just run towards G equals 0. You know what you're doing. Here you have to look for it separately. So this is evidence that such a theory, such a fixed point exists in this lattice theory, and it's motivated by the idea that you're doing an integral of metrics, but there's no rigorous connection for dimensions.
So the reason that you're doing this triangulation story is that you cannot just directly put Einstein's equations.
Well, if you try to if you try to do it perturbatively, you know that you encounter an infinite number of infinities. It's not renormalizable. This can only be seen outside of perturbation. And the only tool you have is numerical simulation.
Yeah, but we do not put Einstein's equations on the lattice theory.
You have the Einstein action restricted to the triangulation. So you're weighting it with the Einstein action. Like here, right? It turns out on these equilateral triangulations, it's very simple. It has a cosmological constant. It has something proportional to the, say, the number of points or the number of triangles. It doesn't matter. These are all related by the Euler characteristic and various other relations. And then there's a curvature. So you're adding this in. You need this. If you didn't have this, you would just have a first order phase transition and no continuum.
That is not part of Einstein.
No, in that sense, you've gone beyond Einstein. Although from a renormalization group point of view, you should always have started with that, right? There's worries about unitarity, but that's second order problem here since we're in Euclidean space. So, but from a power counting perspective, this should all, the R squared terms should be there. You would be surprised if you can construct the theory without them. But you're right, it's a step beyond Einstein in that sense. So you can play games here and talk to cosmologists. You can compute an effective cosmological constant by taking this A, take the cube root of that distribution I just gave you, gives you a measure, roughly speaking, of the scale factor in Euclidean space. So I can construct from it using the Friedmann equations an effective cosmological constant. I can plot that as a function of an effective Hubble constant. And you can sort of see a running dark energy that's coming entirely from quantum effects. Right? There's nothing in here but pure gravity. Right? You can see that it actually enhances as I go to early times. So, this is not my work, so I'm not going to defend it super rigorously, but there are interesting games you can play with these models in terms of even talking about quantum corrections in the early universe coming from these Euclidean path intervals, which are now, regulated on using lattice methods. Yeah. So it naturally gives you a running dark energy. Data, you're on that critical curve, and you're as far down as you can get. So you're your best, finest lattice spacing. I believe that's what it is. So they're interesting games. Time's up now. I'm technically out of time, so I could leave this last topic and try and wrap up, or I could spend. Actually, I have two more topics, so I'm not going to get to you.
We can spend. We started a bit.
Okay, so I'll just try to sketch roughly speaking. So one of the things that you might be interested in is whether you can say anything about this fact that the Higgs seems very unnatural in standard model, right? This is the thing which is responsible for breaking the electroweak symmetry and also by generating Dirac masses for all the standard model firms. So it's a crucial piece of the standard model, but it's by far the ugliest piece of the standard model. In fact, the fact that it has a small bevel like Higgs is not natural. Generally speaking, you'd expect quantum corrections to mix or to make the Higgs sensitive to physics of higher scales, maybe not the Planck scale or the Gut scale, but at least some higher scale, and there's no evidence for that at all in the standard model. So the traditional solutions to this would be to make the theory supersymmetric. That gives you a natural mechanism for keeping the Higgs light. Or you think of the Higgs as some bound state of some new types of degrees of freedom, like technicolor or something like that. That would automatically cut off the high scale of the compositeness scale. But all the results from the LHC so far tell me that the answer to these simple ideas was just no. So all this work that went into SUSY for many, many decades is just useless at this point. Compositeness was always a better argument from a natural perspective, but there's no evidence of that either, right? So one thing is, so that's where we are, right? Nobody knows what to do. So you might say, well, maybe there's some signal here for new non-perturbative physics. So you might ask, as a lattice person, do we understand all the possibilities that there are out there for generating mass, right? So this is all coming from a sort of naive idea that fermion masses look like bilinears. Is that the only possibility? So there are other ideas out there. There's a recent paradigm called symmetric mass generation, which tries to do something different. I'm not sure it resolves the Higgs problem, but at least it's an interesting theoretical kind of perspective. So typically giving fermion mass always breaks chiral symmetries, right? So I can take the fermion and I can rotate it by some phase, which depends on gamma phi. And psi bar psi is just not invariant. So if you think about fermion masses as coming to something to do with psi bar psi, you always end up breaking chiral symmetry, right? Is this the only thing? Is this inevitable? Maybe not. There's a lot of numerical evidence and also some arguments based on anomaly cancellation that fermions propagating in a background of a multi-fermion condensate, which is symmetric under chiral symmetries, can also acquire mass, right? So that's something we can investigate using lattice methods. This is only possible in certain restricted cases. I won't have time, it's really beyond this talk to talk about this, but there are all kinds of anomalies you have to cancel out to make this work. And the reason you haven't known about this before is these things only occur at strong coupling, so you cannot see them in perturbation. So just to give you an idea, this is basically a plot from a simulation of a lattice fermion theory gauged under an SO4 symmetry. This is the 1 over g squared, the gauge coupler constant. This is the 4 fermion condensate. The series starts to confine in this theory around 2.5. As it starts to confine, this 4 fermion condensate builds up. This breaks no symmetries whatsoever, right? So it breaks no symmetries. So this theory doesn't have a pion in it, right? But it does have massive excitations, which are excitations above this 4 fermion ground state. This is an interesting sort of observation in terms of lattice physics. So I get, instead of confining and forming bilinear condensates that spontaneously break chiral symmetries, it forms quartic condensates instead, which don't break chiral symmetries, or at least, right? So there are no. So the bonus here is, of course, this also generates you new excitations. Whatever's responsible for this could give you a new dark sector if you're looking for one, right? But certainly it looks very different from the typical QCD-like scenario. So you might say, what's this lattice fermion theory that I've concocted here, which is able to do this? It's not based, strictly speaking, on Dirac fermions at all. It's based on what I call Kähler fermions. So let me briefly tell you about that. So if you're interested in square rooting the D'Alembert, which Dirac was in 1926, it turns out there's another solution to it, which doesn't involve gamma matrices or spinors or anything else. You can write down an equation for the fermions, which just depends on what's called, this D is what's called the exterior derivative. It's a derivative that naturally acts on forms, on antisymmetric tensor fields, not on spinors. So this psi is an assembly of antisymmetric tensor fields. In flat space, you can show, nevertheless, this actually describes 4 degenerate Dirac fermions. So in flat space, it doesn't really give you anything new. But when you couple it to gravity, its couplings are very different because it doesn't involve spinors. So the gravitational couplings are very different, and the symmetries are different, and that leads to a new anomaly structure too, which can, right? So this is far too technical for this. So I will talk about this next week, actually, in detail. So I'll leave the details out here, but just this is an old observation, it turns out. The nice thing when I go to the lattice, this is all in the continuum, is this theory, unlike the usual Dirac theory, preserves chiral symmetry, both the classical and the quantum level when you discretize it. That's very different from Dirac fermions, where you run into some problems called fermion doubling. This theory doesn't have that problem. If you want to gauge this chiral symmetry, so I'm thinking maybe about Toft anomalies again, I can only do that if the number of these fields is a multiple of 4. So this theory has a natural Z4 discrete chiral symmetry in it, which is not broken at either the classical or the quantum level under discretization. Right? And in fact, if you ask, well, what's the continuum look like when I go back to flat space? It has exactly 16 elements. This is just a historical point, which is kind of interesting. So it turns out this Kähler-Dirac equation had certainly nothing to do with Dirac. It was actually first seen by Landau in 1926. And he wrote a paper which circulated at the same time as Dirac's original paper, where they both computed the fine structure constant in hydrogen. One case using the Kähler-Dirac equation, or what should have been the Landau equation at that point, and then and also Dirac's, and he got the right answer. So he was able to get the fine structure of hydrogen from this equation. Somewhere he must have divided by 4 because he gets 4 Dirac fermions here, not 1. So somewhere he was rooting before it was ever thought about in the lattice community. But anyway, this is a quote from the paper. Finally, we'd like to mention that Dirac, in a recently published work, also treats this problem from the same starting point. Both theories seem to be equivalent apart from the complete difference in methods and equations. However, the precise connection is unclear to us. That we now understand. But, so this thing was lost. This is a Landau paper which has only 30 citations. It was basically lost. I only saw it a couple of years ago. It was rediscovered by Kähler in 1962, and it was again by lattice gauge theorists in the 80s, and then it was dropped. But we've been trying to look at it again in more detail in the context. One of the nice things about this Kähler-Dirac equation, or these Kähler fermions, is that if you ask what's the simplest anomaly-free model based on Kähler fermions you can write down, it turns out it's naturally given by the Hadi-Salon gap theorem. So it has 60 bar fermions, and they arrange themselves automatically as representations of SU4 times SU2 left times SU2 right. So this is a theory where you treat the leptons as a 4th color. It's an old idea going back to the 70s. And you build a left-right symmetric weak interaction out of it. And somehow this has the Higgs down to the standard model with a right-handed neutrino. Right? So one family, the standard model, looks like it has a non-perturbative formulation using these Kähler fermions. It turns out in flat space, these Kähler fermions are well known to the lattice community. They're called staggered fermions there. So there's this hope that maybe you can put the entire standard model on a lattice at some point using staggered fermions and trying to, well, you'll be actually targeting Hadi-Salon, not strictly the standard model, but you might hope that's a great starting point, and simulate the full standard model. And so that's something that is still, very much conjectural. You could do that, but that's what we're. So let me just summarize. This is another example of how lattice can be used for probing BSM physics. So it's had this incredible success over many decades now in supporting the experimental particle physics program. I showed you evidence for that. But of course, lattice quantum field theory is much bigger than QCD. You can use it to uncover any non-perturbative physics in many different BSM scenarios you can come up with, whether it be SUSY or mass generation, maybe dark matter things, even direct approaches to quantizing Einstein gravity, and hence even be able to talk maybe to cosmologists at some point. So the lattice suggests new approaches. You saw that for quark confinement. It's also true with these Kähler fermions. They're very natural from a lattice perspective because they allow you to be, they can be discretized without mutilating the symmetries of the theory. And they can be coupled to supercomputing in the end to reveal non-perturbative structure if you're lucky. And so there's potentially many sort of exciting things to do. Sorry, I've gone a little over.
Thank you for the talk. Any questions? So you mentioned that is allowing that they put the leptons as a 4th color.
Yeah, that's an old idea.
Don't you need like 5 colors because of the neutrinos?
No, you just need
the 4.
Yeah, this is what I'm saying is that if you look at the natural structure of these Kähler-Dirac theories when they go back to the spinor formulations, they naturally have an internal SU2 cross SU2 structure, it turns out. And because I need 4 copies, because it is an anomaly cancellation, there's a natural SU4 in the game. And in fact, the representations just match the original Hadi-Salon representations in the 1974 paper. where it's like 4, 1, 2 plus 4 bar 2 1. And so those are natural spinor representations that emerge from the Kähler theory in the flat space limit. So it's just, that's the simplest Kähler theory that makes sense. Turns out to be a gut theory we already knew about.
Simon, you mentioned earlier about why 3 generations.
Yeah. I don't have any Y3.
Yeah, so
Offline, I could give you a numerology argument based on Kähler fermions, but I don't dare do that at all.
okay.
I
I
say I
thought you
don't
were going to talk about that.
and I said I wouldn't talk about that.
Oh, you said
Yes, and you were kind of hinting that you wanted to talk about.
okay. Yeah, then I have one more.
Okay.
So, by the way, these Paddy Salam done naively is a chiral gauge theory. And it's been a long goal of Lattice field theory to talk about chiral gauge theories. There's been a barrier to doing that, rooted in theorems that go back 20 or 30 years. So this seems like doing an end route around some of those old no-go theories.
So there is, you showed a figure with the normal polymer phase or something.
Yeah, the gravity stuff.
Yeah, so why it's sort of plain, why 2 dimensions, 3 to 4, why that type of transition?
Oh, wow. I
Yeah.
don't think Jack has an idea. It's seen by many groups who've done this.
Right.
But it's very easy to see why there's a collapsed phase, where basically the geometry collapses a little. Almost every point talks to every other point. So it's Planckian scale. That's easy to see. It's not so obvious where the branch polymer comes from, but people have conjectured it's due to the Alden boundedness problem of Euclidean quantum gravity, where the conformal mode sort of stretches things out. And so you get a sort of branch polymer structure. But that's, I think, just speculation.
So can we say that there could be a phase in our universe where this,
You could.
which was conformal or something?
Which was, I mean, if you're asking whether the universe on a very large scale could look like a branch of all places, good.
Yeah.
If it's beyond the,
Penrose has this idea of what's it, conformal cyclic cosmology.
I have heard of it.
So the universe expands and at some point it becomes conformal or something.
It's still online. I'm not saying anything.
Okay. So yeah, anyway, so that
Yeah, I mean, this is very different from his Weyl curvature hypothesis, which does make sense. Which is that the observation that the early universe appears to be much simpler than hence the Weyl curvature is 0. That's why we have a thermodynamic over time. But I think that's very different.
right, so yeah, maybe we missed.
Yeah. Nobody knows what those phases are about.
Jeff, or
Yeah.
So in this, when you remove the Catterall phenomenon,
Yes.
this no pi isn't that like pi ones being measurable, but
Well, but you don't want, you're trying to come up with scenarios for mass generation which don't look like conventional. So the normal Higgs phase is based on a pretty conventional symmetry rate account. Right, so what you're doing here, I'm not saying it resolves any immediate problem you have there. What we're doing really is a theoretical study where revealing that there are other mechanisms for mass generation which don't necessarily involve breaking parallel symmetries. They may or may not be useful for figuring out what replaces the Higgs, if anything. Right, but I wouldn't say we have any model at the moment which you could put in place so that Higgs mechanism and suddenly resolve all problems. And I don't know. Maybe you'll never have something like that. But right now, it's just this observation, which actually came from the condensed matter community again, originally. This symmetric mass generation originated there. And it's sort of been expanded from there to particle physics and even to mathematical physics. So people understand some of the anomaly cancellation conditions that you need to make this go in terms of what they call die-free anomalies. So these are you take some theory of, say, Weyl fermions and you put it on very exotic manifolds with interesting topology, and they give you constraints. When you can do that consistently, it gives you new constraints on the theory. And those are formulated as anomaly cancellation constraints for discrete symmetries. And so it's a discrete symmetry that plays a role here, actually. But it's much simpler and has more. Well, next week I'll, for those who are here, I'll say a bit more about the anomaly structure of these things. So these are gravitational ones, but not the usual ones.
We went back to your graph with the background.
Oh, yeah.
I mean, it doesn't have to show, but I was wondering, isn't that also
Yeah.
and what's the experimental issue?
I think they're harder. People still work on them. I think the statistical errors on the blue balls are much larger than they are on the regular hadrons. The blue balls mix with all meson states anyway, so they're not really a separate sector. And so when people do as analysis, they have to take into account possible blue ball mixing as well. So I'm not the person to really answer that in any detail, but it is a very active area of research. I think the errors are much worse than they are for some of the hadrons that show.
Experimental talent.
I think because they mix with the vacuum state very as well. So there are just it's difficult to write down a turbulent. Technically, it's difficult to write down what are called the turbulating operators. Lattice operators are coupled with right column numbers coupled to the blue ball that you could extract signals with good signal to noise ratio. But I'm certainly not an expert.
But that's basically what I'm using for comparing the lattice predictions. I mean, there should be some points there that have not seen experimental.
Right, I think that's true, but I don't know the exact status. Yeah, people are always trying to find global candidates, right, to match with these. The
I just haven't followed it recently.
Neither of I is the honest truth.
So, see, holographic applications, is the connective theory that you use, isn't it just capturing the sector, preserving supercharge, or is it?
So if I'm in flat space, it doesn't much matter. If I'm just living on the torus, it's just a change of variables, which is a better starting point to discretize. Right. So we're not restricting just to the topological sector. So not just states in either div by Q. It's basically the Marcus GL twist is used. So you get remove all the spinors from the theory. So you end up with just antispectral tensors, which are basically Kähler fields, actually. That's how I bump into these things, is actually the Susi optics. Because the natural fermions, the way fermions naturally appear in a lattice theory is sort of forms, because you know exactly how to put them on a lattice. Line, sides, links, triangles, heptahedral, whatever. So the Kähler fermions come out very naturally. It turns out that basically the things that live on the links, if you want, the analog of the U matrices, are combinations of the gauge field of the scalars. That's what we like. So it's basically A plus IB, where B is the scalars. So they're no longer unitary matrices, they're complex matrices. But you have so it's extremely natural lattice construction to see it, but it basically gives you the non-Marcus twisted for the naive. And so the Q that you preserve is precisely a Q that appears in theory. But you just have this exotic lattice, you put fermions and all the obvious geometrical objects, you put gauge links and all links, but they're complex now, and then you write down an action which is Q exact plus the Q closed piece. Which is very natural, that's very close too. And you just you can do that all maintaining lattice gauge invariance and the world supercharge. So and it obviously describes exactly the right number of fermions corresponding to 16.
Why to thermal boundaries?
You can do that. Yeah, we've done that in fact.
But place it on some algebraic manifold.
Right, then it's not so clear that you're doing the same thing. Right. So we mostly live on a torus, where it's basically flat space. If you start changing the manifold, then of course you're deforming the theory in non-trivial ways. But we certainly have played the game of putting one of the directions further. That's how you get the black hole results. So you might argue at that point you're doing something slightly different. You stick to this twisted version. But it certainly seems the most natural form from a purely lattice perspective. If I was to say, in fact, the only theory we know how to discretize in 3+1 dimensions, preserving any amount of supersymmetry on the lattice, is n = 4. It's uniquely selected. So it's a very special theory, supersymmetric theory from a lattice perspective.
Say comment, but I'm just asking that NFT provide ways to adapt. When I'm down.
Well, part of what I showed you is that in some sense the naive answer is yes. You can try to come up with ways of discretizing this the finite pattern of metrics by replacing metrics by something by a lattice itself, but the degrees of freedom of a lattice is triangulation. But you can also sit on a regular lattice and you can try to treat it as an ordinary lattice gauge theory. There are efforts in that direction too, where I replace SU3 by something like, say, SO4, which is Euclidean Lorentz transformations. It's a local gauge symmetry. And so people have played that game a little bit. I'd say that's less mature, but it's certainly not hopeless. I don't know how to do it when I have a Lorentzian signature, because then the intervals aren't convergent. If I stick to compact gauge theories, I know exactly what. So that means Euclidean quantum gravity. So there are formulations that do that, actually. And I've even actually played a little bit of them years ago. So you can treat it as an ordinary quantum field, where the spin connection is the gauge.
So I also using this. It's called the or Python, this lattice pattern.
Not Python. Python's a bit too slow.
Python is just so
You have to write this stuff in C.
it's a software that you can use.
Sure. There are lots of public codes for lots of this stuff. Actually, UCD has a lot of public codes. But even like for our N=4 stuff, there's a public code on GitHub, which anybody can use. Things like that. A lot of people can still make mistakes. Yeah. Of course, having the code is not enough. You need to know how to use it. And if it's a parallel code, you need to have access to a supercomputer to run it. The nice thing about the triangulation stuff is there are no supercomputers that can run that efficiently because your mesh is changing. So it's a huge computer science problem to distribute the dynamical mesh. So in practice, what people do is they stick on single nodes, and maybe they parallelize in a dumb way on configuration space. Or if you're Jack, there are fancy algorithms where you run streams independently and then swap between streams sometimes when you make moves. So there are all kinds of sophisticated games you can play numerical once you have basic ideas.
I think, was there still a question there? Let's go through.
So you had the very nice example of G-2 solves with the lattice calculations and able to extend the sort of precision of the results. I know that in the QCD phase diagram is a big question regarding the critical point. And I know there's some.
This is finite density.
Yes.
Yeah, so finite density is tough with lattice UCD because you have a sign fault. So that's why I want to So I told you about is all done at zero chemical potential by a sign fault. Literally, the lattice sizes that are used these days like 124 cubed by 400. I mean, just ginormous lattices that fit in these big machines in their running funds. And the code is super optimized. For a guys who just were postdocs who just specialize in writing assembler to do the particular multipliers. So there are really big collaborations in doing this. That's not stuff I had ever thought.
Do you know what the sort of status is of options?
Oh, in finite density? Oh, I could find some out for you. I'm not sure I can quote something offhand. But if you want to know, I can give you a reference. People to talk to that should do that. Yeah, it's much, much harder. And people have some idea about how to proceed, but it's much harder. Once you multi-level as a sign problem, it's no longer an efficient problem. So you have to think about other ways of doing it. I know she worked on complex algebra, and that's another way of doing things like finite density. There are a few other ideas, slash extendals. There's also analytic, and I think you start off in a place where you don't have a sign problem, you analytic and solve. That sort of works but there's no really good boilerplate way of doing finance instead. So the nuclear physics people, that's them in focus. And that's one argument for doing quantum computations, going back to quantum formulations, using quantum information. It's because maybe you can do progress on things like density, but you can't do so well. You need to be more powerful.
Okay, I think with that, it's a good point to end. Simon will be around, I think, for a bit longer, so you can start. And that also brings us to the end of the talk. So thanks for attending. And this is a yearly thing. So next year, I think it will be held in the University of Pretoria. But please keep a lookout for the advertisement. I guess you guys will hear from customers from the source themselves. But for the others, please join us again next year. Yep. Your traveling car, not many, but you are. Then it's okay. And okay.
So I think I'll be going. I don't think I'll be able to join. I understand. The kids have like Christmas concerts, prepare food for the vegetables.
Totally.
What's it? But we'll celebrate. This one? We'll celebrate also.
Yeah, exactly. Exactly. Yes, thanks a lot for bringing me to. It was great.
They're like one of the
No, I'm just saying. Well,
Yeah, I wonder
but roughly. Might be 12.
Yeah, so right, because the way you put it is
What that is.